This particular lecture is mainly on fuel metering in SI and CI engines. At first, we will discuss about SI engine fuel metering. The SI engine meters fuel into the air stream of amount dictated by the speed and by the load. This is usually done by either carburetor or by fuel injector. It must satisfy the requirements of the engine over its entire operating regime. The optimum air-fuel ratio for a SI engine is that which gives required power output with the lowest fuel consumption, consistent with smooth and reliable operation. The constraints of emissions control may dictate a different air-fuel ratio and may also require the recycling of a fraction of the exhaust gases each year into the intake system. Strategy A: optimized for maximum torque, part load efficiency and ideal stability. And strategy B: optimized for emissions reduction, stoichiometric operation. Look at this. Here is the lead mixture and here is the lean mixture. And it is in equilibrium state when phi is equal to 1. Enrichment to improve ideal stability. Enrichment at high load to maximize torque to prevent knocking and reduce exhaust temperature. Lean for lower fuel consumption. And here, no easier to improve ideal stability, easier to decrease NOx emission and pumping loss, no easier to maximize airflow for power. Mixture requirements are different for full load and for part load operation. At full load, complete utilization of the inducted air to obtain maximum power for a given displaced volume is the critical issue. For part load operation at a given speed, efficient utilization of the fuel is the critical issue. With a few exceptions, mixture formation using a carburetor is no longer the preferred approach. However, many SI engines still use carburetors for mixture formation. SI fuel injection systems. Number A: single point or throttle body injection, TBI. This is the figure for TBI. Number B: multi-point or port fuel injection, MFI or PFI. This one. And number C, the last one, direct in-cylinder injection or gasoline direct injection, GDI. And this one is for GDI. Normally, electronic fuel injection EFI system uses electronic engine control EEC, sometimes called the electronic control module ECM. Injectors are fitted with solenoid operated valves. EFI system contains, among others, fuel injector, different sensors, throttle position sensor, oxygen sensor, intake air temperature sensor, manifold absolute pressure sensor MAP, etc. Relay controller, fuel pump, inertia switch. TBI system of fuel or throttle body injection system of fuel metering is a lower cost injection system. It employs one or two low pressure injectors that inject fuel into the air stream above the throttle plate. Fuel is measured in response to calibrations of airflow, air temperature, engine speed and other signals. The injection duration is controlled with an exhaust gas oxygen sensor to provide a stoichiometric mixture to each cylinder. The fuel supply pressure is about 2 bar, which is absolute. A central fuel injection system. Number 1, pressure regulator. Number 2, injector. Number 3, air temperature sensor. Number 4, fuel inlet. Number 5, fuel return. Number 6, insulator plate. Number 7, throttle. In the PFI or MFI system, that means port fuel injection or multi-point fuel injection system, there are as many injectors as there are intake valves. Fuel is injected directly over the intake valves. The advantages are increased power and torque through improved volumetric efficiency. Fuel distribution is more uniform, more rapid engine response to changes in throttle position, more precious control of in-cylinder air-fuel ratio. Schematic of a port fuel injector. Major components are valve housing, injector needle and its pintle, the armature, helical spring, solenoid coil. The needle is lifted about 0.15 mm when the solenoid is excited. And injection pressure is 3 to 7 bar. And look at this schematic of port fuel injector. Here you can see the pintle, spray hole, needle, stopper plate, armature, connector, valve seat, valve body, injector body, solenoid coil, and spring. Here are two more schematic. First one is for schematic of fuel injector nozzle. Here you can see the air inlet hole, the mixing nozzle, auxiliary air for automation, and adapter. And in the next figure you can see schematic of port fuel injection system or PFI system. Look at this, fuel is injected through this, and here is the moving auxiliary air. A more recent and advanced system of SI injection system is GDI system. GDI system has two clear operational advantages. Number 1, fuel is injected directly into the cylinder, which provides more rapid and precise control of mixture preparation. And number 2, fuel distribution within the cylinder can be controlled and stratified, which allows the engine to operate at a lean mixture, especially at part load. GDI system has some other advantages, which are, since the fuel is vaporized within the cylinder, thereby reduce the air temperature, allows a higher compression ratio without the possibility of knocking, and more air can be inducted, thereby increasing the full load torque. Charge stratification allows a linear operation, which in turn reduces the SFC. However, the fuel system is slightly costlier. Stratified operation requires fuel injection during the latter part of compression stroke, while homogeneous stoichiometric operation requires fuel injection during the intake stroke. Fuel injection pressure for homogeneous mixture varies between 5 and 15 MPa, that means 50 to 150 bar, and for stratified mixture between 5 and 20 MPa, that means 50 to 200 bar. Two major categories of mixture preparation in DI stratified charge SI engine are: number A, widely spaced injector and spark plug, wall and air guided, and number B, closely spaced injector and spark plug, spray guided. Fuel spray can be of different types: swirling type, asymmetric swirl type, or fan shaped spray. Look at this schematic. This is for number A, which is widely spaced injector. You can see the injector here, and spark plug, wall and air guided. Okay, this is the spark plug and this is the injector. That is widely spaced. You can see the distance between spark plug and injector in this figure. And this is for number B, which is closely spaced injector and spark plug, spray guided. Look at this. This is the injector and this is the spark plug. And there is a few distance between these two, and there is a wide distance between these two. So these are the basic difference between these two types of fuel injectors. For GDI engines should have the following features. The injected liquid fuel must be atomized into small droplets and appropriately dispersed throughout the appropriate region of the cylinder or combustion chamber. For homogeneous operation, a uniform distribution is needed, and for stratified operation, the spray must provide a readily combustible mixture around the spark plug and within a restricted volume. A GDI swirl type fuel injector and the signals that activate the fuel injection is shown in the following figure. Here are two figures. First one is a GDI swirl type fuel injector, and next one is the signals that activates this. Number 1, electrical connection. Number 2, spring. Number 3, coil. Number 4, nozzle needle. Number 5, guide washer. Number 6, swirl plate. Number 7, seat washer. Number 8, adjusting nozzle. Number 9, housing. Number 10, solenoid armature. Number 11, shim. Number 12, o-ring. Number 13, valve housing. And the last one, number 14, Teflon ring. And here you can see the signal, the current, needle lift, injected fuel quantity, pre-magnetization, injection time, a lot of this. So this ends some basic information about SI engine fuel metering. Now we will discuss about CI engine fuel metering in short. CI engine fuel metering. CI engines can be broadly classified into categories. First category is direct injection or DI diesel engine. Fuel is injected directly into the single open combustion chamber. The next category is indirect injection or IDI diesel engine. Fuel is injected into a pre-chamber which is connected to the main chamber via a nozzle or one or more orifices. They can be further classified into swirl chamber type and turbulent pre-chamber type. Indirect engines are usually used in smaller CI engines. Nowadays, high-speed direct injection engines replace the indirect ignition engines. There are two schematic. First one is for 3 types of direct ignition diesel engines, and next one is for 2 types of indirect ignition diesel engines. The cylinder pressure at injection is in the range of 50 to 100 bar. However, the injection pressure can be in the range of 1000 to 2000 bar depending on the engine size and type of combustion system used. Orifice hole size, though, which the fuel is injected, is typically in the range of 0.2 to 1.0 mm in diameter. Diesel fuel injection systems are high pressure for 2 reasons. Number 1, to atomize the fuel into small droplets to enable rapid evaporation. And number 2, to traverse the combustion chamber in the time available so as fully utilize the air charge. There are 2 methods of fuel injection. First one is air injection. Highly compressed air is injected through the fuel nozzle into the cylinder. Rate of fuel admission can thus be controlled by varying the pressure of injected air. And number 2, solid or airless injection. Liquid fuel is injected directly into the combustion chamber and also known as mechanical injection. So these are the 2 types or 2 methods of fuel injection. Main components of CI fuel injection systems are fuel tank and primary filter, low pressure fuel feed pump, main filter, often two-stage filter, high pressure injection pump, governor to control the amount of fuel to be injected depending on engine speed and load, low and high pressure pipes. There are a number of types of modern fuel injection systems. Common rail injection systems (CRS), unit injector system (UIS), distributor type injection system, electronic injection system. Common rail system (CRS) is a widely used system. It allows greater freedom to control the fuel injection process. The functions of fuel pressure generation and fuel injection are separated by a common rail or an accumulator. A high pressure pump feeds the common rail which feeds the fuel injectors. Injection pressure of 1400 to 1800 bar can be achieved in this system. This is a schematic of common rail injection system where you can see different colors with indicated different things. The blue colors indicated pre-supply pressure, the red color indicated high pressure, the blackish color indicated return line pressure, and the yellow color indicated fuel, and these lines are indicated electrical connection. All these things are schemated in this figure, which is a common rail injection system. Unit injector system or UIS is another method of fuel injection. It combines the pump and injector into a single unit. The unit is driven by engine camshaft. The start of injection and fuel quantity is controlled by a solenoid valve in the injector. It has a precise control of injection timing and fuel quantity. Injection pressure of about 1000 bar can be achieved in this system. This is a schematic of unit injector system where you can see the roller type rocker arm, ball pin, pump piston, piston spring, injection cam, high pressure chamber, O-rings, heat insulating seal, cylinder head, solenoid valve, needle injector, solenoid valve, fuel return line, retraction piston, fuel supply line, injector spring, injector needle damping element, and injector needle. So this is the figure of unit injector system. Distributor type fuel injection system is mainly used in smaller CI engines. The components of this system include a high pressure injection pump, an over-speed governor, and an injection timer. It has one pump plunger and barrel which meters and distributes the fuel to all the injection nozzles. High pressure is generated by the plunger. It can operate at higher speed. In electronic fuel injection system, there is an ECU or ECM and a number of different sensors like the SI engine fuel injection systems. The unit can be included as a part of other injection systems described before. This is a schematic of distributor fuel injection system. Here you can see the high pressure pump CP1, rail pressure sensor, PCV, other actuators, fuel filter, pre-filter, control unit, accelerator pedal, engine speed, crank, engine speed, cam, injector. Here you can see two different colors. One is red colors which is for high pressure, and the one is yellowish color which is for low pressure. So this is the figure of distributor fuel injection system. There are a number of different types of pumps used in the CI engine injection systems. Axial and radial piston distributor pump, inline injection pumps, distributor type fuel injection pumps. So these are the different types of pumps used in the CI engine injection systems. There are two schematic. In the first schematic or first figure, you can see this indication. Two injector, delivery valve spring, delivery valve, fuel inlet, intake port, fuel sump, to that control stick, lug attached to plunger, plunger return spring, helix on plunger, spill port plunger, control rack and housing. And in the next figure, you can see the 5 process: number A, BDC, number B, end of injection, number C, BDC, number D, end of injections, and number E, stop. This is a figure or schematic of volume control of an inline injector pump. 3 different types. First one is for no flow, next one is for partial flow, and the last one is for full flow. Look at this first one, where you can see the inlet piston pump cylinder hole open and fuel return, control rod, regulator housing. Next figure, partial flow. You can see here the angled edge, hole partially open and partially flow amount, movement of the control rod. And in the last figure, for full flow, to the injector valve, consumable volume, full throttle, full flow amount, and control rod at full throttle. So this is the figure of volume control of an inline injector pump. There are also 2 figures. First one is for standard and 2 spring injectors, where you can see the fuel supply, bar filter, fuel spill, injector body, compression spring, plunger, nozzle adjusting nut, compression spring 1 for pre-stroke and compression spring 2 for main stroke, secondary piston stop. And here the total head is equal to H1 is plus H2. Okay, so and this is for standard and 2 spring injectors. And in the next figure, you can see the piezo injector with direct control of the spray needle, where you can see the adjusting device, piezo actuator, high pressure connection, fuel spill, injector housing, plunger, and injection nozzle. Here you can see the injection nozzle designs. Pintle nozzle with inclined front view, and pintle nozzle with inclined surface side view. Multi-hole nozzle with conical sac hole, multi-hole nozzle with cylindrical sac hole, and multi-hole nozzle with valve seat directly or nozzle holes. And in the right side there you can see the Pintox nozzle. Here you see pin, needle and auxiliary hole. And this is the last page of this lecture. Recap again, this lecture is on mainly 2 types of fuel meterings. One is fuel meterings in SI engines and the another is fuel meterings in CI engines. This particular lecture is about on this topic: internal combustion engine fuels, their properties and tests. Fuels for IC engines. The main fuel for IC engines is derived from crude petroleum, which is a mixture of many hydrocarbon compounds. Crude oil is made up almost entirely of carbon and hydrogen with some traces of other species. It varies from 83% to 87% carbon and 11% to 14% hydrogen by weight. The crude oil mixture which is taken from the ground is separated into component products by cracking and or distillation using thermal or catalytic methods. It is entirely possible but not economically feasible to convert almost completely the crude petroleum into gasoline and diesel fuel. Fractionation of crude petroleum. Crude oil, butane and lighter hydrocarbons, straight run gasoline, naphtha, kerosene, light gas oil, heavy gas oil, and straight run residue. Temperature vaporization curve for typical gasoline mixture. Front end volatility components are useful for cold starting. High-end volatility components increase the volumetric efficiency. This is a graph. Here you can see the x-axis define percent evaporated and a y-axis define temperature degree Celsius. There are two figures. First one is a fuel technology and the next one is investment for 1 lakh BBI per day refinery versus octane rating of gasoline produced. Here you can see some indicator like catalytic cracking, alkylation, thermal reforming, catalytic polymerization, thermal cracking, straight run, reforming, all straight run gasoline, all cracking done catalytically, and research octane rating with 1 mLTL. There is a graph. X-axis we define percent evaporated and a y-axis we define temperature, degree Fahrenheit. And there are 6 different lines. Line A, number 2D diesel fuel, which is good grade. Line B, number 1D light distillate, high speed diesel engine and JP5 jet fuel. Line C, kerosene. Line D, JP4 jet fuel. Line E, automotive gasoline, and line F, aviation gasoline. Families of IC engine fuels. First one, alkanes. The paraffin family, alkanes, open chain structure, aliphatic hydrocarbons with general formula CnH2n plus 2. This is the chain reaction. The critical compression ratio, CR, for audible knock in an SI engine decreases rapidly as the length of the chain of the normal members is increased. Thus, the normal paraffins in the volatility range of gasoline are poor SI fuels. The knock ratings of the fuels are in rough proportion to the self-ignition temperatures. In progressing downward with higher carbons, the suitability of the fuels for SI engine progressively decreases and for CI engines progressively increases. Thus, hexadecane or cetane has a low self-ignition temperature and therefore it is a good fuel to prevent knock in a CI engine. Interestingly, the air-fuel ratio AFR for the chemically correct mixture is essentially constant even though the fuel structure and phase change. Because of this constancy, various fuels can be supplied to SI engine without changing the carburetor adjustment. Also that the energy content per unit volume of mixture is essentially constant and therefore the power output of the engine is not affected by a change in fuels unless knock is present. The fuels of this family are stable, clean burning and do not attack gaskets or metals. Next one, alkenes. The olefin family alkenes, the monoolefins have open chain structure, aliphatic olefins with general formula CnH2n. This is the chain reaction where you can see the double bond. The physical properties correspond closely to similar compounds in the paraffin family and are also clean burning and a higher octane rating. Because of the free bond, the olefins are chemically active and unite readily with hydrogen to form the corresponding paraffin or naphthene. When they unite with oxygen, they form an undesirable residue, gum, which can cause smoke. Next one, alkyne. The diolefin family, alkyne diolefins have two double bonds with a general formula CnH2n-2. This is the chain reaction where you can see two double bonds or a triple bonds in between carbon. These are undesirable fuel components because upon storage, reactions take place that lead to coloring of the fuel and also to the formation of a cloudy gum. Acetylene has one carbon-carbon triple bond. Additional members of the alkyne series comprise open chain molecules similar to higher alkenes but with each double bond replaced by a triple bond. Next one, cyclanes. The naphthene or cycloparaffin family, cyclane, have the same general formula as the olefins but are saturated, ring structure compounds. These are desirable components of motor gasoline. So this is the chain reaction, and the basic formula is CnH2n, similar to alkene. Next one, benzene. The aromatic family, benzene derivatives, ring structured hydrocarbons with general formula CnH2n-6. This is the chain reaction of this aromatic family, and the formula is CnH2n-6. You can see here there are 6 carbon and 6 hydrogen, because when N is 6, C6, and H 2 into 6, that means 12, minus 6, that means 6, that means C6H6, and this is the chain reactions of C6H6, which is benzene. These are excellent gasoline fuels and can be selectively produced by catalytic cracking or by thermal cracking at high temperatures, almost 1200 degrees Fahrenheit. Benzene or benzol is an excellent blending agent to raise the octane ratings of low-grade fuels. The aromatics have the highest densities of the hydrocarbon and therefore have the highest heating values per unit volume. These fuels are stable in storage, smoky in burning with high solvency powers. Next one, the alcohols. The alcohols are a partial oxidation product of petroleum with a chain structure of the general formula ROH, where R is the paraffin group. They have good anti-knock qualities with octane ratings in excess of 100. Alcohols absorb water from atmosphere. They also require a different AFR than gasoline. And this is the chain reaction of monohydric alcohols, CnH2n plus 1 OH. This is the basic formula of the alcohols group. Gas or natural gas can be associated or unassociated. The composition of gas varies widely, with methane usually predominating from 60 to 98%, and with percentages of ethane and other paraffins along with carbon dioxide, helium and nitrogen. A sour gas is one which contains hydrogen sulfide. Otherwise, it is called sweet gas. Before the gas enters the pipeline, it must be sweetened, dehydrated, and liquid hydrocarbon removed. Synthetic or substitute natural gas, CNG, are produced from solid wastes, petroleum crudes or fractions, or coal. Liquefied petroleum gas, LPG, may be propane, butane, or a mixture of the two. Natural gas and LPG are excellent fuels for the SI engine, home and gas diesel with low emission pollutants. LNG and CNG are the two other versions of natural gas. Self-ignition and octane number. The temperature above which the fuel-air mixture self-ignite is called the self-ignition temperature, or SIT. Octane number, ON, is a fuel property that describes how well a fuel will or will not self-ignite. Depending on the test conditions, ON can be researched on, RON, or motor on, MON. Anti-knock index, AKI, is the arithmetic average of RON and MON. Fuel sensitivity, Fs, is equal to RON minus MON. The reference scales. The reference scale to measure SI NOx has been established by arbitrarily selecting two primary reference fuels. Isooctane 2,4-trimethylpentane has been arbitrarily assigned an octane rating of 100, while N-heptane has been assigned an octane rating of 0. The reference scale for measuring CI NOx is based upon hexadecane and heptamethylonine as primary fuels, with assigned values of 100 cetane and 15 cetane respectively. Characteristics of modern gasoline. Modern gasoline may be made up of straight-run gasoline from fractional distillation, cracked gasoline from catalytic cracking, reformate from catalytic reforming, alkylate and polymerized gasolines produced from gases, with some butane or propane to achieve the desired rate vapor pressure. The two most important characteristics of gasoline are its volatility and octane number. The gasoline sold in the market is a blend of a number of products produced in several processes. Desirable properties of gasoline. NOx characteristics. The octane rating. The fuel should have an octane rating to fit the engine requirements. The tests for determining octane number are performed using the ASTM CFR Cooperative Fuel Research Engine, a variable compression ratio engine. High octane fuels enable high compression ratios to be used, give increased power output and improved economy. Volatility, expressed in terms of the volume percentage that is distilled at or below fixed temperatures. If the fuel is too volatile, it will start the engine readily. When it is used at high ambient temperatures, the fuel is liable to vaporize in the fuel lines and form vapor locks. And if the fuel is not sufficiently volatile, the engine will be difficult to start, especially at low ambient temperatures. Typically, a compression ratio of 7.5 requires 85 octane fuel, while a compression ratio of 10 would require 100 octane fuel. In general, the fuel with the lowest distillation temperatures is the best. Dilution of the lube oil may occur when the fuel condenses or fails to vaporize in the engine. The volatility also influences the cold start fuel economy. Gum and varnish deposits. The fuel should not deposit either gum or varnish in the engine. Corrosion. The fuel and the products of combustion should be non-corrosive. Cost. The fuel should be inexpensive. Additives used in gasoline. In order to achieve the required properties of gasoline, as well as for other purposes, various additives are used. Anti-knock. To reduce or eliminate the knock in SI engine, previously TEL or TML are used along with some scavengers. Nowadays, MTBE or TBA are used. Deposit modifiers. To alter the chemical character of combustion chamber deposits and to reduce surface ignition and spark plug fouling, usually phosphorus and boron compounds are used. Antioxidants are used to prevent gum formation. Amines of amount 0.5 to 6.5 kg per 1000 bbl. Detergents are used to prevent deposits in carburetor and manifold. Alkyl amine phosphates of amount 5 kg per 1000 bbl. Lubricants. To lubricate valve guides and upper cylinder regions, 0.1 to 0.5% light mineral oils. Metal deactivators. To destroy the catalytic activity of tracers of copper, amine derivatives of amount 0.5 kg per 1000 bbl, and anti-rust agents to prevent rust and corrosion arising from water and air, fatty acid amines, sulfonates or alkyl phosphates of amount 0.5 to 6.5 kg per 1000 bbl. Anti-icing agents to prevent gasoline freeze from water in fuel and throttle plate icing from water in air, methyl alcohol and isopropyl alcohols of about 1% each are used for the purpose. Sometimes, a surface action agent such as ammonia, salts, or phosphates about 0.005% is also used. Equivalent air distillation (EAD). Gasoline used in engines is a complex mixture of many hydrocarbons and other molecules. Calculating the vapor-air ratio is thus very complicated. An experimental procedure is generally used to determine the vapor-air ratio, known as the equivalent air distillation (EAD). In this method, the fuel is allowed to evaporate into a stream of air moving through a long heated tube. The exit vapor ratio is measured as a function of the fuel-air ratio supplied, the total pressure, and the exit temperature. Characteristics of CI engine fuels. The most important characteristic of diesel fuel is the Seton number, which indicates how readily the fuel self-ignites. Usually, the self-ignition temperatures of the normal paraffins decrease as the length of the chain increases. Paraffins have Seton rating, which vary almost linearly with the length of the chain. Thus, the straight-run gasoline fuels, which might be poor SI fuels, are desirable for CI engine. The other important characteristic is the viscosity, especially for lower grade fuels used in larger engines, may need to have heated fuel lines. Another problem with diesel fuels is that at low temperatures, the high molecular weight components can precipitate to form waxy deposit called filter plugging point. The requirements for a good CI fuel cannot be as simply stated as those for gasoline because of the added complexity of the CI engine from its heterogeneous combustion process, which is strongly affected by injection characteristics. NOx characteristics. If an engine runs on a fuel with too low Seton number, there will be diesel NOx. Diesel NOx is caused by too rapid combustion and is the result of a long ignition delay period, since during this period, fuel is injected and mixes with air to form a combustible mixture. Ignition occurs only after the pressure and temperature have been above certain limits for sufficient time, and fuels with high Seton numbers are those that self-ignite readily. The minimum Seton number of the good grade diesel fuel is 50 and for the other is 45. Starting characteristics. The fuel should start the engine easily, requires high volatility to form readily combustible mixture, a high Seton rating so that the self-ignition temperature is low, smoke and odor. The fuel should not produce smoke or odor after combustion. Corrosion and wear. Should not cause corrosion before combustion or corrosion and wear after combustion, directly related to sulfur, ash and residue contents of the fuel. Handling is should be liquid that will readily flow under all conditions. Measured by the pour point and viscosity of fuel, the fuel should also have a high flash point, since an advantage of the CI engine is its use of fuels with low fire hazards. Flash point of diesel fuel is at least 35 degrees Celsius, while that for gasoline and kerosene are about minus 40 degrees Celsius and 30 degrees Celsius respectively. Additives in diesel fuel to improve the Seton number are referred to as ignition accelerators. Their concentrations are greater than those of anti-knock additives used in petrol. By adding 1% of amyl nitrate, C5H11 or NO2 increases the Seton number by about 6. Ethyl nitrate C2H5ONO2 and ethyl nitrite C2H5ONO are other effective substances. Ignition delay is most pronounced at slow speeds because of the reduced temperature and pressure during compression. Cold starting can be a problem and other severe conditions. Heaters may be needed. Also, excess fuel may be injected. Sometimes volatile fuels with high cetane numbers such as ether can be added to the intake air. Sometimes a cetane index is used as the only information needed is fuel viscosity and density with no need for engine tests. The cetane index can be used only for straight petroleum distillates without additives. Other fuels that are suitable for diesel engines are derived from coal and vegetable oils. Tests for diesel. Viscosity exerts a strong influence on the shape of the fuel spray. High viscosity causes low atomization and high penetration of the spray jet. In small combustion chambers, the effect of viscosity may be critical. Gravity. Normally, the API gravity is used for fuels. The API gravity is defined in terms of the specific gravity. API gravity 141.5 divided by specific gravity at 60 degree Fahrenheit minus 131.5. In general, high API gravity is simply high cetane fuels. Sulfur. Corrosion and increased wear is caused in the engine along with carbon deposits on the piston and rings or deterioration of lube oil due to the presence of sulfur in fuels. Carbon residue is the result of the fuel burnt with a limited amount of oxygen. High carbon residues contribute to deposits in the combustion chamber and around nozzle tips, thus interfering with the spray shape. Ash. The ash content is a measure of the abrasiveness of the products of combustion that could cause wear in the engine. Water and sediment. Of all specifications for diesel, the cleanliness factor is probably the most important because of the precisely fitted parts in the fuel pump and nozzle. Flash point is the lowest temperature of the fuel that allows inflammable vapors to be formed. It is important for safety purposes and serves as a measure of the fire hazard. Distillation. Range should be as low as possible without unduly affecting the flash point, the burning quality, or the viscosity of the fuel. Ignition quality. The ease of igniting the fuel in the engine by auto ignition is called the ignition quality of the fuel. The diesel index number DI has been empirically found to correlate approximately the cetane number of most commercial fuels, which is defined as DI, that means diesel index number, is equal to aniline point into API gravity divided by 1000. The aniline point is defined as the minimum temperature at which equal volumes of aniline C6H5NH2 and the oil are miscible. That means form a single phase upon mixing. The DI and the cetane rating for the fuel for most high-speed diesels should be the order of 50 to 60. Cetane ratings below 40 may cause exhaust smoke with increased fuel consumption and loss of power. Pour point is determined by cooling a sample of oil in a test jar until, when the jar is displaced from the vertical to horizontal position, no perceptible movement of the fuel will occur within 5 seconds. It is important only when the engine is to be used at low temperatures. This lecture is about this particular topic: exhaust gas analysis and air pollution. Air pollution from IC engines. Spark ignition and diesel engines are a major source of urban air pollution. Emission characteristics of IC engine: nitrogen 72.1%, oxygen and inert gases 0.7%, H2O 13.8%, carbon dioxide 12.3% and pollutants 1.1%. Raw emission without catalyst in percent by volume, and this picture is for SI engine, and this one is for diesel engines, where nitrogen 73.8%, oxygen 9%, H2O 9%, carbon dioxide 8%, pollutants 0.2%. The spark ignition engine exhaust gases contain oxides of nitrogen, that means nitric oxide, NO, small amounts of nitrogen dioxide, NO2, collectively known as NOx, carbon monoxide CO, and organic compounds which are unburnt or partially burnt hydrocarbons HC. Piston blow-by gases and fuel evaporation and release to the atmosphere through vents in the fuel tank and carburetor after engine shutdown are also sources of unburnt hydrocarbons. Use of alcohol fuels in either petrol engines or gasoline engines substantially increases aldehyde emission. Gasoline and diesel contain sulfur. Gasoline in small amounts less than equal 600 ppm by weight. Diesel fuel in larger amounts less than equal 0.5%. The sulfur is oxidized or burnt to produce sulfur dioxide SO2, of which a fraction can be oxidized to sulfur trioxide SO3, which combines with water to form a sulfuric acid aerosol. Effects of pollutants. Four principal effects of pollutants in the troposphere are altered properties of the atmosphere and precipitation. Effects on local areas include reduced visibility resulting from the presence of carbon-based particulate matter, sulfates, nitrates, organic compounds, and nitrogen dioxide, increased fog formation and precipitation, resulting from high concentrations of sulfur dioxide that form sulfuric acid droplets, reduced solar radiation, and altered temperature and wind distribution. On a larger scale, GHGs may alter global climates. Also, acid rain produced from SOx and NOx emissions affects lakes and susceptible soils. Harm to vegetation. Vegetation is harmed by the phytotoxicants SO2, peroxyacetyl nitrate, PAN, C2H4 and others. Phytotoxicants destroy chlorophyll and disrupt photosynthesis. Soiling and deterioration of materials. Acid and alkaline particles, in particular those containing sulfur, corrode paint, masonry, electrical contacts, and textiles, while ozone severely deteriorates rubber. Potential increase of morbidity or sickness and mortality in humans. Pollutants can aggravate pre-existing respiratory ailments. The occurrence of both acute and chronic bronchitis can be correlated with sulfur dioxide and particulate matter. Pollutants and their origin. So this figure is reaction mechanisms in the combustion chamber. Look at this: air, nitrogen and oxygen, fuel CXHY, here air fuel mixture, and reacting elements nitrogen, oxygen, carbon and hydrogen. From this we get nitrogen NOx, oxygen H2O, carbon dioxide, carbon monoxide RCSO, CXHY and H2. Mechanics of pollution formation. Sources of pollutant formation in SI engine: oil layer, quench, intake valve deposits, liquid fuel, combustion chamber deposits, crevices, and here is NOx CO. There are two figures. From the first figure we can say in the x-axis here this is defining fuel or air equivalence ratio or air fuel ratio. In the y-axis it defines NO, CO and HC concentration. This one is for NO, nitrogen. This one is for HC, hydrocarbon. This one is for CO, carbon monoxide. Here the lean mixture, rich mixture, and here remains the stoichiometric. And from the next figure we can say x-axis we define equivalence ratio phi, y-axis we define amount of emissions in exhaust flow. This one is for lean, this one is for rich, and here is the line. This is for hydrocarbon, this is for NOx, and this is for carbon monoxide. Causes of hydrocarbon emissions. Hydrocarbon emissions arise from uncombusted and partially combusted hydrocarbons. These components can originate from both the fuel and the lubricants. Non-stoichiometric air-fuel ratio, incomplete combustion, crevice volume, leakage past the exhaust valve overlap, deposits on combustion chamber walls, oil on combustion chamber walls. Mechanics of pollution formation for hydrocarbon, where fuel is 100% and here goes 91%, which is combustion chamber, carbon dioxide, H2O, carbon monoxide and pollutants, only fuel, and here 9%, which is hydrocarbon formation. From this we can get this mixture. So this is the figure, which is SC or hydrocarbon formation mechanisms in SI engine combustion. In the diesel engine, the process of hydrocarbon formation is more complex. In general, a CI engine has about 98% combustion efficiency, with only about 2% of the hydrocarbon fuel being emissions. CI engines also have hydrocarbon emissions for some of the same reasons as SI engines too: oil deposit absorption, oil film absorption, crevice volume, etc. The most important sources of hydrocarbon are the periphery of the spray. The mixture composition lies outside the ignition area, that means too lean, and the inner spray area. The mixture composition is too rich. Mechanisms or mechanics of pollution formation for hydrocarbon. So this figure is for hydrocarbon emission climbs practically linearly with the volume of the blind hole. So look at this. First one is valve seat or nozzle hole. Next one is conical sac hole, and the last one is cylindrical sac hole. Causes of carbon monoxide emissions. Carbon monoxide is produced in an engine when it is operated with a fuel-rich equivalence ratio. Typically, the exhaust of an SI engine will be about 0.2% to 5% carbon monoxide. Maximum carbon monoxide is generated when an engine runs rich, such as when starting or when accelerating under load. If an extremely lean mixture lambda greater than 1.0, increased carbon monoxide develops again due to the lower temperatures and incomplete combustion in the area near the wall of the combustion chamber. CI engines that operate over lean mixtures generally have very low carbon monoxide emissions. Mechanics of pollution formation, carbon monoxide. Here you can see the hydrocarbons, RAS, NOx, qualitative representation of diesel engine combustion and pollutant formation. Causes of NOx emissions. Exhaust gases of an engine can have up to 2000 ppm of oxides of nitrogen. Most of these will be nitrogen oxide (NO), with a small amount of nitrogen dioxide (NO2) and traces of other nitrogen-oxygen combinations. NOx reacts in the atmosphere to form ozone and is one of the major causes of photochemical smoke. NOx is produced by high flame temperature. Its formation also depends on pressure, air-fuel ratio, and combustion time within the cylinder. The amount of NOx generated also depends on the location within the combustion chamber. The highest concentration is formed around the spark plug, where the highest temperatures occur. Because they generally have higher compression ratios and higher temperatures and pressure, CI engines with divided combustion chambers and indirect injection (IDI) tend to generate higher levels of NOx. If ignition spark is advanced, the cylinder temperature will be increased and more NOx will be created. Mechanics of pollution formation (NOx). Here are two different graphs. First one is concentration of NOx versus time, and the next one is mole fraction of NOx in exhaust versus spark timing degrees (BTDC). Thermal NO, nitrogen oxide, or extended Geldovis mechanism. N2 plus O, NO plus N. N plus O2, NO plus O, N plus OH, NO plus H. These relations are very temperature sensitive. These are more prominent in CI engine because of higher compression ratio. Causes of particulate emissions. The exhaust of CI engines contains solid carbon soot particles that are generated in the fuel-rich zones within the cylinder during combustion. Maximum density of particulate emissions occur when the engine is under load at full load. Up to about 25% of the carbon in soot comes from lubricating oil components, which vaporize and then react during combustion. The rest comes from the fuel and amounts to 0.2 to 0.5% of the fuel. High boiling point components found in the fuel and lubricating oil condense on the surface of the carbon soot particles. This absorbed portion of the soot particles is called the soluble organic fraction (SOF), and the amount is highly dependent on cylinder temperature. At light loads, cylinder temperatures are reduced and can drop to as low as 200 degrees Celsius during final expansion and exhaust blowdown. Under these conditions, SOF can be as high as 50% of the total mass of soot. Dilution with EGR lowers NOx emissions but increases particulates and hydrocarbon emissions. Controlling pollution formation (NOx). It follows that the NOx concentration of the exhaust gas from SI engine is primarily a function of temperature and composition and secondarily time, and is decreased by decreasing the combustion temperature, by decreasing the oxygen available in the flame front. The total peak NOx value for a given engine load and speed invariably occurs at an equivalence ratio little more than 1.0. NOx is reduced in modern engines with fast burn combustion chambers. Controlling pollution formation (hydrocarbon). Hydrocarbon concentrations of the exhaust gases from an SI engine should be decreased by high temperature of the exhaust gas, more oxygen in the exhaust, smaller mass in quench envelope, and more time for reaction. Control of engine emissions (SI engine). Mixture formation. The air-fuel ratio of the mixture in the combustion chamber has the greatest influence on untreated emissions. The emissions of carbon monoxide and hydrocarbon are lowest in the slightly lean range of lambda is equal to 1.05 to 1.1. Untreated NOx emissions are highest in the range. An equivalent air-fuel ratio for all cylinders is another prerequisite for low emissions. This requires highly precise measuring of the fuel to all cylinders. Valve control. A central spark plug and the symmetrical 4-valve combustion chamber form is optimum for low pollutant combustion. A small valve overlap, small valve stroke, and late intake time allow emissions to be greatly reduced in the partial load range. Cylinder shut-off in engines with a large number of cylinders also decreases fuel consumption and hence carbon dioxide emissions. Exhaust recirculation. When exhaust emissions are fed to the intake manifold, even distribution to all cylinders must be ensured. Exhaust recirculation rates greater than 15% yield somewhat higher hydrocarbon emissions and poorer idling. Compression ratio. High compression improves thermal efficiency, but the peak combustion temperature is increased, which in turn produces higher NOx emissions. Combustion chamber design. In addition to the geometry that affects the bore-to-stroke ratio, the surface, volume, and squash area, other parameters influence emission behavior. Measures to lower untreated hydrocarbon emissions are variable swirl formation in the intake port and regulated engine temperature control. Ignition. The design of a spark plug in the combustion chamber influences the shape of the flame front and hence also the formation rate of nitrogen oxides. Late ignition produces low NOx emissions. A long spark duration produces low hydrocarbon emissions. Control of engine emissions, CI engine, combustion procedure and combustion characteristic. Flatter and wider piston cases allow unhindered jet expansion. This development has been supported by multiple hole fuel injection nozzles, reduces the amount of fuel deposited on the valve. Charge losses can be reduced by increasing the swirl. Supercharging. Turbocharging or supercharging is by far the most efficient option for reducing all pollutants components. Variable turbine geometries, sequential supercharging, and charge air temperature regulated according to load can reduce for fuel consumption and especially NOx emissions. Fuel injection systems and fuel injection procedures. The best strategies must be taken for the most important parameters such as fuel injection pressure, nozzle shape like jet position, projecting mass, number of nozzles, fuel injection quantity, pre-injection, injection spacing, secondary injection, injection time and cutoff time. A small pre-injected quantity of less than 1 mm³ minimizes NOx and particle emissions. Secondary injection reduces particle emissions while NOx emissions remain the same. A very short cutoff time especially lowers hydrocarbon emissions. Injecting water reduces NOx by up to 25% in engines with an excessively high combustion temperature, but this also worsens carbon monoxide and hydrocarbon emissions. Valve control. 4 valves now appear to be the best approach for diesel engines because of the injection nozzle position. Variable valve control and phase shifters are now used. Exhaust recirculation. There is a notable increase in the number and size of particles as the exhaust recirculation rate increases. Combustion chamber design. Basically, the same design rules hold true as for spark injection engines. Wide, flat combustion chambers with a slow swirl are preferred when there is a large piston displacement. Emission control devices, PCV system. Look at this figure. Here you can see the blow-by, closed oil filter cap, fresh air in through this, tube to air cleaner, this one, tube to intake manifold, and this is the PCV valve. Emission control devices, EGR system. So there are two figures. Look at this first one. Here you can see the throttle valve, air intake manifold, exhaust gas, diaphragm, EGR valve, spring, and vacuum hose. And the next figure you can see the throttle valve, ported vacuum switch, EGR valve, exhaust gas, intake manifold. Look at this figure. Here is a clear indication of exhaust gas, deflector, diaphragm, timed manifold vacuum, restriction, vacuum chamber, control valve closed, filter screen, spring control valve, actuating diaphragm, back pressure sensor, airflow in. And here you can see the control valve open and exhaust gas to intake manifold. Emission control devices, TWCC. A catalytic converter, more specifically a three-way catalytic converter, TWCC, reduces the emissions of hydrocarbon, carbon monoxide, and NOx. It has an oxidation chamber and a reduction chamber. In the oxidation chamber, hydrocarbon and carbon monoxide and oxygen react to form H2O and carbon dioxide. And in reduction chamber, NOx is reduced to N2 and O2. Reactions in TWCC occur in presence of catalysts. Oxidation catalysts are platinum, palladium, and rhodium. Other lesser catalysts are copper, vanadium, iron, cobalt, nickel, manganese, chromium, and their oxides. Generally, same catalysts are used for reduction reactions. Reduction reactions are more complicated. There is a figure of emission control devices. Look at this. Here you can see the manger, connecting pipe, hanger, resonance chamber, pipes, air injection tube, catalytic converter, clamp, oxygen sensor, hung, exhaust pipe, clamp, extension pipe, muffler, clamp, resonator, and tailpipes. Here are some details figure of TWCC, that means three-way catalytic converter. Look at this. This is figure A, 12-bed pellet type catalytic converter. This one, and this is figure B, three-way honeycomb type catalytic converter. Conversion efficiency of catalytic converters as a function of converter temperature has been shown in the figure. This one, catalytic converter efficiency versus temperature graph. The temperature at which the converter becomes 50% efficient, this line, is often called the light of temperature. Okay. Volume of the ceramic structure of a converter is generally about half of the displacement volume of the engine. This is the figure of conversion efficiency of catalytic converters as a function of fuel equivalence ratio. In the x-axis, we define the equivalence ratio. Here is the lean mixture, and here is the rich mixture, sorry. And in the y-axis, we define catalytic converter efficiency percentage. So there are three different lines. This is for hydrocarbon, this is for NOx, and this one is for carbon monoxide. Emission control devices, CI engines. Compression ignition engine systems are equipped with particulate traps in their exhaust flow to reduce the amount of particulates released to the atmosphere. Traps are filter-like systems, often made of ceramic in the form of a monolith or mat, or else made of metal wire mesh. Traps typically remove 60 to 90% of particulates in the exhaust flow. To reduce flow restriction in the traps after continued use, particulate traps are regenerated when they begin to become saturated. Regeneration consists of combusting the particulates in the excess oxygen contained in the exhaust of the lean operating CI engine. Emission control in CI engines. DPF, diesel particulate filter. composed of a preliminary catalyst and a main filter made of carbides. Soot particles collected in the filter are ignited by hot combustion gases. Because temperature of combustion gases in the outlet collector is in the range of 150 to 200 degrees Celsius and the ignition temperature of soot is approx 550 degrees Celsius, temperature of combustion gases is increased by burning of some additional fuel. This is a picture of diesel particulate filter for CI engines or DPF. This one is sintered metal filter for CI engines or SMF. This is the figure of chemical reactions during soot burning in a catalytic soot filter. And this is the last figure of this lecture, where you can see the 1224 VDC supply, display module, pressure sensor, control module, fuse box with global plug driver, pump module, diesel fuel tank, engine, diesel particulate filter, where temperature, 3 different temperature sensors are existed. The red lines are fuel lines, the black lines are data or power cables, and the blue lines are for pressure lines. So that's it. This particular lecture is about idealized cycles and processes. Ideal air standard cycles. An IC engine is not a heat engine in the thermodynamic definition of the term. It is not a closed system and the working fluid does not execute a thermodynamic cycle. To make the analysis of the engine cycle much more manageable, the real cycle is approximated with an ideal air standard cycle. Assumptions are as follows. Air alone is the working fluid. Heat loss is considered zero while the heat capacity of the air is assumed to be constant. The real open cycle is replaced by a closed cycle. The combustion process is replaced with a heat addition term Q-in. Exhaust process is changed into a heat rejection process Q-out. Intake and exhaust strokes occur at constant pressure. Compression and expansion processes are isentropic. The heat addition processes are constant volume for Otto cycle and constant pressure for diesel cycle. A limited pressure cycle or dual cycle is one where the heat addition process is a combination of constant volume and constant pressure. Heat rejection process for all cycles is a constant volume process. All the above mentioned processes are considered reversible. Here are 3 different cycles. First one is air standard Otto cycle. This one air standard diesel cycle, and this one air standard limited pressure or dual cycle. Thermodynamic relations. Since we assume that the combustion efficiency is unity, indicated thermal efficiency eta T is given by eta T Otto is equal to W net by Q in. Indicated mean effective pressure I MEP is expressed as I MEP is equal to W net by VD. W net is the indicated work and is the sum of compression and expansion stroke work. For constant specific heats, applying the ideal gas loss, the efficiency expression can be written as eta T Otto is equal to W net by Q in is equal to 1 minus 1 by RC power K minus 1. A similar expressions for diesel cycle can be derived as follows. Eta T diesel is equal to W net by Q in is equal to 1 minus 1 by RC power K minus 1 into beta power K minus 1 divided by K into beta minus 1, where RC is equal to compression ratio, K is equal to Cp by Cv, and beta is equal to cutoff ratio. That means V3 by V2, or change in volume that occurs during heat addition. A similar relation can be obtained for the limited pressure or dual cycle. Eta T dual is equal to W net by Q in is equal to 1 minus 1 by RC power K minus 1 into alpha beta power K minus 1 divided by K alpha beta minus 1 plus alpha minus 1, where alpha is equal to pressure ratio, that means P3 by P2. Cycle comparison. Overall performance characteristics for each of these cycles are summarized in the following table. So there is a table where we will find these types of data of eta Fi IMAP by P1, IMAP by P3, Pmax by P1, constant volume, limited pressure and constant pressure. And there is a graph of three different lines: constant volume, limited pressure and constant pressure, where RC, that means compression ratio, is 12, K is equal to 1.3, P3A by P1 is equal to 67. The air standard cycle with constant values for Cp and Cv is unreal, since Cp and Cv increase with temperature increase while K decreases. When these variations are included in the analysis, the pressures and temperatures throughout the cycle are radically changed in value. There is a graph in the x-axis, and on the y-axis we define different things, and there are three types of lines. One is constant pressure, another is limited pressure, and the other is constant volume line. For the same cylinder input and the same compression ratio, eta T auto greater than eta T 12 greater than eta T diesel. So there are two types of graph. First one is pressure versus specific volume, and the next one is temperature versus enthalpy. For the same compression ratio and with the same heat input, the thermal efficiency is the highest for the constant volume cycle and lowest for constant pressure cycle. In the former, the cycle allows the most complete expansion and attains the highest efficiency because all the heat is added before the expansion process is underway. For constant compression ratio and heat input, eta Ti is equal to 1 minus Qr by constant, eta Ti auto greater than eta Ti actual greater than eta Ti diesel. And there are two different types of graphs. First one is pressure versus specific volume, and next one is temperatures versus enthalpy. On the basis of the constant heat input and maximum pressure, constant pressure cycle is the most efficient, while constant volume cycle is the least efficient, because less heat is rejected in the case of diesel cycle. Here, eta Ti diesel greater than eta Ti actual greater than eta Ti auto, and there are two types of graph. First one is pressure versus specific volume, and next one is temperature versus entropy. For constant maximum pressure and output, eta Ti is equal to W by Qa, that means W by W plus Qr is equal to constant by constant plus Qr. Eta Ti diesel greater than eta Ti 12 greater than eta Ti auto. For constant maximum pressure and temperature, eta Ti is equal to W by Qa is equal to 1 minus Qr by Qa, where eta Ti diesel greater than eta Ti 12 greater than eta Ti auto. And there are two types of graph. First one is pressure versus specific volume, and next one is temperature versus entropy graph. SI engine cycles at part throttle and OAT. OAT means full load. There are two types of graph. First one is pressure versus specific volume for SI engine cycles part throttle, and next one is pressure versus specific volume for SI engine cycles at full load. Fuel air cycle analysis. It is assumed that the composition of unburnt mixture is not changed and the burnt gas mixture is in equilibrium. The resulting cycles are then called fuel air cycles. The sequence of processes and assumptions are 1 to 2. Reversible adiabatic compression of mixture of air, fuel vapor, and residual gas without change in chemical composition. 2 to 3. Complete combustion at constant volume or limited pressure or constant pressure without heat loss to burn gases in chemical equilibrium. There are three types of cycle. First one is fuel air Otto cycle. Next one, fuel air diesel cycle, and this one, fuel air limited pressure or dual cycle. And every cycle there are two different graphs. First one is for pressure versus specific volume graph, and next one is temperature versus enthalpy graph. So every cycle there are two types of graph. Process 3 to 4, reversible adiabatic expansion of the burned gases which remain in chemical equilibrium. Process 4 to 5 to 6, ideal adiabatic exhaust blowdown and displacement processes with the burned gases fixed in chemical composition. Process 6 to 5 to 1, ideal intake process with adiabatic mixing between residual gas and fresh mixture, both of which are fixed in chemical composition. Results of cycle calculations. For constant volume fuel air cycle, efficiency mainly depends on the compression ratio and equivalence ratio. Given an equivalence ratio, the efficiency increases with increasing CR, that means compression ratio, provided that an appropriate value of K is chosen. Efficiency increases as phi decreases. Due to the presence of more air, the burn gas temperature and specific heats decreases, resulting in increased value of over the expansion stroke. For a given volume expansion ratio, the burned gases expand through a larger temperature ratio prior to exhaust. Therefore, per unit mass of fuel, the expansion stroke work is increased. The MEP is high when phi is in between 1.0 and 1.11. For a value of phi less than, that means that the decreasing fuel mass per unit displaced volume more than offsets the increasing NTI. For a value of phi greater than, that means that the decreasing eta Ti more than offsets the increasing fuel mass. Over-expanded engine cycles. For 4-stroke engines, the exhaust blowdown pressure is higher than the exhaust pressure. Thereby, the available energy of cylinder gases is lost. Had the cycle been extended beyond 0.4 to 0.7, the indicated work would have been increased. The cycle is called an overexpanded cycle. Overexpanded engine cycles. Atkinson cycle. In the air standard Atkinson cycle, air is allowed to expand to atmospheric pressure. Exhaust valve is not opened until that time. A greater amount of expansion work is thus obtained with an increase in engine thermal efficiency. There is a graph of pressure versus specific volume. Overexpanded engine cycles. Miller cycle. Another such cycle is the Miller cycle, a modification of Atkinson cycle. Air intake in this cycle is unthrottled. Thus, a major loss is eliminated, especially true at part throttle. There is a graph of Miller cycle, which is a pressure versus specific volume graph. The limitations of Atkinson cycle. A complicated linkage system is much reduced or eliminated in modern Miller cycle. In actual engines, variable valve timing mechanisms replace the linkage system of Atkinson cycle. The pump work is essentially zero, resulting in higher thermal efficiency. The compression ratio is given as RC is equal to V7 by V2, and the expansion ratio is RE is equal to V4 by V2 or V4 by V3. An extremely important factor for this cycle is that the intake valve must close exactly at 0.7. A typical value of compression and expansion ratios for Miller cycle engines are 8:1 and 10:1 respectively. Miller cycle engines are often supercharged or turbocharged with peak intake manifold pressure of 150 to 200 kPa. Air standard approximation of two-stroke cycle. The first figure is a pressure versus volume graph, which is for air standard approximation of two-stroke SI engine, and the next one is a pressure versus volume graph, and which is for air standard approximation of two-stroke CI engine. Comparison with real engine cycles. Modest differences in pressure during intake and the early part of the compression process result from the pressure drop across the intake valve during the intake process and the closing of the intake valve. The expansion stroke pressures for the engine fall below the fuel-air cycle pressures. The enclosed area on the PV diagram of the actual cycle is, therefore, 80% of the enclosed area of an equivalent fuel-air cycle PV diagram. This ratio is generally used to estimate the performance of actual engines from fuel-air cycle results. Finite combustion time. In an SI engine, combustion typically starts 10 degree to 40 degree before TC, is half complete at about 10 degree after TC, and is essentially complete 30 degree to 40 degree after TC. Peak pressure occurs at about 15 degree after TC. In a diesel engine, the burning process starts shortly before TC and the pressure rises rapidly to a peak some 5 degree to 10 degree after TC, since the initial rate of burning is so fast. The final stages of burning are much slower and combustion continues until 40 degree to 50 degree after TC. Real SI engine cycle. The real cycle is shown here in the process 1 ABC1. Look at this 1 ABC1, this one, okay. YZ is an isentropic line passing through B. YZ, this line. Ignition starts at A and ends at B. Starts here and ends here. Exhaust valve opens at C, this point. That starts the exhaust blowdown. Losses in real SI engine cycle. Time loss. The real curve usually lies well within the ideal curve. The hashed area to the left of curve AB and the below the curve YB is called time loss. Heat loss. During the compression process, there are heat losses through the cylinder wall that are not very significant. After combustion, however, the temperature is much higher, and as the gas starts to expand, a significant amount of heat is lost to the wall. The hashed area above curve BC is called heat loss. Exhaust blowdown loss. The area with dots in it, that means to the right of C1, is called exhaust blowdown loss. In order to get rid of the burned gases from the cylinder, the exhaust valve is opened 50 degree to 60 degree before BC. The burned gases leave with a lot of enthalpy. Crevice effects and leakage. As the cylinder pressure increases, gas flows into crevice. A few percent of clearance volume, such as the regions between the piston rings and cylinder wall. The flow reduces the mass in the volume above the piston crown, and the flow is cooled by heat transfer to the crevice walls. In premixed charged engines, some of this gas is unburned and some of it will not burn. Leakage in a well-designed and maintained engine is small. All these effects reduce the cylinder pressure during the latter stages of compression, during combustion and during expansion below the value that would result if crevice and leakage effects are absent. Incomplete combustion. In spark ignition engines, the hydrocarbon emissions from a warmed-up engine are 2 to 3% of the fuel mass under normal operating conditions. Carbon monoxide and hydrogen in the exhaust contain an additional 1 to 2% or more of the fuel energy, even with excess air present. Hence, the chemical energy of the fuel which is released in the actual engine is about 5% less than the chemical energy of the fuel injected. There is a table of availability losses in naturally aspirated diesel. There are some loss mechanisms and loss fraction of fuel availability. So some data are available there. There is a graph. Injected fuel conversion efficiency as a function of compression ratio for ideal gas constant volume cycle dashed lines. There are so-called dashed lines, and fuel air cycles, the solid lines. Okay. Also shown are available engine data for equivalence ratio given. This are okay. So that's it.